Hey folks, welcome back. Today we're going to talk about another test for the convergence of series, and this is a really important test called the ratio test. It's possibly the most important test we're going to look at, and it literally looks at the ratio of one term to the next. And if you think about an infinite series, we're just adding a bunch of terms together, and what this is saying is the n plus 1th term divided by the nth term, so one term to the next, that ratio has to be less than 1. And if that's the case, the thing will converge absolutely. So let's imagine n's really large. So if n's really large, I expect this to be the limiting value to be approached, right? So this should be close to the limiting value. And so for convergence, we want that to be less than 1. For large enough n, this is what we kind of expect. So this is, an approximate kind of thing. In other words, what I'm saying is the n plus 1th term has to be smaller than the nth term. And we know, in fact, that a series diverges if those terms aren't going to 0 in the long run. So for convergence, we expect these numbers as we go along, eventually, for large enough n, we expect these numbers to be getting smaller. And that's really what this ratio test is telling us. It says if you have a series and the limit of the absolute value of the ratio of the n plus 1th to the nth term, if that's less than 1, then the series converges absolutely. And that's really powerful. So this is important to note, this is a test for absolute convergence. And if something converges absolutely, then it's going to converge just as it stands. In other words, a series converges absolutely means that the sum of the absolute values converges. And so that if that's true, then the sum of the terms themselves converge. And we had a theorem to that effect. Essentially, it's because here I'm adding up positive numbers. Here, some of them might be negative, so that value's got to just be smaller, right? This ratio test is a really powerful idea. It builds on what we've talked about before. Let's have a go at some examples. Okay, here's our first example. The series here is the sum of n squared over 2 to the power of n. And so, starting with n equals 1, we get 1 squared over 2 to the power of 1. So that's just a half. And the next term is 2 squared over 2 squared. Well, that's just 1. And the next term is 3 squared over 2 cubed. And the next one is 4 squared over 2 to the power of 4. And you get the idea, right? The nth term here is n squared over 2 to the power of n. But this is an infinite series, so it goes on forever. Don't ever leave those dots out, because those dots mean that it's an infinite series. Without them, if I were just to stop writing, then I've got a finite series, and that's a very different beast. Finite series have to converge, because converge doesn't really mean anything. Right? If I give you a finite number of real numbers and say, add these all together, you're going to just get some real number. So this idea of convergence only makes sense for infinite series. So there's our series, and we want to use the ratio test to see if this converges. And as a reminder, the ratio test involves this fundamental property. So let's calculate that limit. So the limit as n tends to infinity of a sub n plus 1 over a sub n. I'm going to use that idea I kind of alluded to in the earlier example where we had the earlier test where we had the limit comparison test. I'm going to write down a sub n plus 1 and a sub n, and then I'm going to plug them in here, right? Another way of thinking about this is a sub n plus 1 over 1, if you like, multiplied by 1 over a sub n. And 1 over a sub n flips a sub n. So rather than writing it out in an awkward way, I'm always going to write it out directly for this n plus 1th term. So this will be n plus 1 squared over 2 to the power of n plus 1. Make sure you know where this is coming from, right? Literally, if this is my nth term, then I'm replacing every value of n with n plus 1. And when I do that, it turns into the n plus 1th term, right? I get an n plus 1 there, I get an n plus 1 there, I get an n plus 1 there, because every n turns into an n plus 1. And then I'm going to write down 1 over a sub n, because that's, I'm dividing by a sub n here, and 1 over a sub n is the reciprocal of a sub n. So I can just plug that in here. This is 2 to the n divided by n squared. And our job now is just to simplify that. So I'm going to group the like terms here. So all I did is rearrange a little bit. So the 2 to the n's go together, so I wrote them there, and the polynomials go together, I wrote them there. And what we're going to do is just simplify this. And it's not hard to simplify it. I'm going to move on to the next page so that we can see this whole thing build up. So just laying this out, you can see what we did. We calculated this quantity. We've got the absolute value signs. We'll deal with that at the end. But we took a sub n plus 1, the reciprocal of a sub n, we've multiplied them together. You know, I'm doing the division, but it's simplifying the algebra that way. And now I can just simplify, right? I've got 2 to the power of n up there, and I can cancel that with the 2 to the power of n down there, because remember what 2 to the power of n means. If I've got 2 to the power of n plus 1, that's the same as 2 to the power of n times 1, 2 to the power of 1. And so I'm cancelling those two, and so that's leaving in the denominator a single 2, and so I'm writing that down there. And then this one, well, this is n plus 1 over n, all inside the same brackets, if you like. I mean, I'm doing this in multiple steps. You can do it more quickly. But just using, just dividing here, this is 1 plus 1 over n, all right, times 1/2. And then we can take the limit of this thing. So as n goes to infinity, 1 over n goes to 0. So this is 1 plus 0 times 1/2. And the absolute value of that, well, that's just a half. So there we go. It's a half. And if we go back to the ratio test, it says that if this limit, which they're calling rho in this test, if this limit is less than 1, then the series converges absolutely. So let me just note that that's less than 1. And so this thing converges absolutely. The series we were looking for converges absolutely. And in fact, these terms in the series are all positive, so that means that the series converges as well, because absolute convergence and convergence are the same thing for a positive series. So we've used the ratio test, and I should say that here. So by the ratio test, because you should always do that when you're writing this down, by the ratio test, that converges absolutely simply because that limit is less than 1. And that's kind of the steps you go through to apply the ratio test to every problem. Later in this section, we'll talk about when it's appropriate to apply certain kinds of tests, what you should be thinking about as you're looking at a series. But right now, let's just go through the application process. Here's our next example. If we kind of look at this, you can see what the values in the series are. When we read this, we see the nth term, right? The nth term here is just given to us. So in this case, a sub n is just that ratio with minus 1 to the power of n. And n starts at 0. So our a sub n starts at 0 here. That's fine. If we start writing it out, when we plug in 0, e to the 0 is 0. And remember way back when we defined 0 factorial to be 1. So this first term is just 1. The next term is going to be negative, and it's going to be e over 1 factorial, which is 1. And the next term is going to be positive, and it's going to be 2 factorial. Right, I can write that as 1 factorial. The next one's going to be e cubed over 3 factorial. The next one's going to be e to the 4 over 4 factorial, and the signs are alternating. So there's our series. Remember, 1 factorial is just 1, 2 factorial is just going to be 1 times 2, 3 factorial is 1 times 2 times 3. These are basic functions in what we've been dealing with. We're going to use them a lot more in the next couple of weeks. So be comfortable with the factorial function. It's just the product of the first n terms. We're going to use the ratio test. So the same question, does this series converge? Absolutely. Does it converge? Conditionally, does it just converge? Is it divergent? So this is an alternating series, so it could in fact be conditionally convergent or it could diverge. But let's look at the limit, because the ratio test requires us to look at that limit. It's always the same limit. We don't care whether the series starts at 0 or 3 or minus 12, because what we're looking at is the ratio of one term to the next as n gets large. So it really doesn't matter how it starts. So we just need to find the general term and plug it in. So in this case, our general term is going to be, well, here we've got a sub n. So let me write down a sub n plus 1. We're just going to go through here and replace the n's with n plus 1. So a sub n plus 1 is going to be minus 1 to the power of n plus 1. It's going to be e to the power of n plus 1 divided by n plus 1 factorial. So there are our terms. And now I'm just going to plug them in. So I'm going to get minus 1 to the power of n plus 1, e to the n plus 1 divided by n plus 1 factorial. There's our a sub n plus 1 term. And then writing in our next term, our a sub n term, we get the right product. So this is the reciprocal of a sub n, right? I'm dividing by a sub n here, so I wrote in the reciprocal. And I'm really putting that minus 1 here. That's part of the numerator, right? That minus 1 there is in the numerator, so I'm really thinking about it as being on top. Really doesn't matter a great deal, but I've put it in the denominator here. And now I can cancel powers, right? So just like last time, we're going to group like terms so that we can do some simplification. The least interesting are the 2 minus 1. So I've got minus 1 to the power of n plus 1, minus 1 to the power of n. Then I've got e to the power of n plus 1 in the numerator, and e to the n in the denominator. And then we've got n plus 1 in the numerator, and then n plus 1 factorial in the denominator. And so we end up with that. And we have to simplify this. So what this is an integer power of of just the number e. So this literally is just e multiplied by itself n times. Sorry, if we're talking about the top one, n plus 1 times. And on the bottom, we've just got it n times. So they're going to cancel out and leave us just with a single e in the numerator. Similarly here, we've got minus 1, n plus 1 times on the top, and we've got n of them on the bottom, so the n are going to cancel, and we're just going to be left with a single minus 1 to the power of 1, and then a single e to the power of 1. And now what do we do with the other bit, the n factorial over n plus 1 factorial? That takes a little bit more thinking because we don't know those factorials quite as well. So when all else fails, let's just write out the definition, right? N factorial is the product of the first n positive integers. So here's the term, we've got a minus e, and on the top we've got n factorial, which is the product of the first n integers. And in the denominator we've got n plus 1 factorial, which is the product of the first n plus 1 integers. And if you notice, we've got the common first n integers on the top and on the bottom. And so what's left here is e divided by that n plus 1. I've got rid of the negative sign because it's inside the absolute values. Right? So in fact, I don't need absolute values here anymore because e over n plus 1, that's a positive number. So I'm just taking the limit of this. The absolute values have got rid of the negative sign because the absolute values make things positive. And then we just need to take this limit, e coming from here, and n plus 1 in the denominator coming from there. Well, e is a fixed number, right? E is just 2.714. It's just a number. And it's divided by n plus 1. N's getting larger and larger. That must be 0. And because that's 0, ratio test tells us immediately this series converges. So we've got the working here. Make sure you know how to work that out, how that comes about. But let's go to the next page and sort of summarize. So since the limit as n tends to infinity of that ratio is 0, and 0 is definitely less than 1, so it follows by the ratio test that this series we were looking at is absolutely convergent. And since it's an alternating series, we know that it's therefore convergent as well, because of our theorem in the previous section, which said that any series that's absolutely convergent is also convergent. So this gives you an idea how to use this ratio test. Again, an important idea we saw in this one that wasn't in the previous one is the use of these factorial functions. We haven't talked about them a lot. We've talked about them a little bit, and they're going to become more important in the coming weeks. So make sure you're comfortable with where this is coming from and how these came about, how this calculation came about, where this term is coming from. Because that's really the crux of this calculation. Once you've taken the limit, you can just quote the ratio test, convince me that because that limit is less than 0, this is absolutely convergent. Here's another example. Same question. Is this convergent? Absolutely convergent. Does it diverge? You should recognize this immediately. This is our old friend, the harmonic series. And if you remember nothing else from those earlier sections, you should remember what the harmonic series does. But let's use the ratio test to think about what's going on here. Using the ratio test means looking at the limit of this ratio. So in this case, we get the limit as n tends to infinity of the absolute value of, well, let's go over here. A sub n is just 1 over n. And a sub n plus 1 in this case must be 1 over n plus 1. So we get 1 over n plus 1. That's our a sub n plus 1 term. And then we're going to multiply it by 1 over a sub n. That's the next term. And 1 over a sub n must be n over 1. That's just the reciprocal of this. So 1 over a sub n is n over 1. We take the reciprocal. Now we need to take that limit. This is the limit as n tends to infinity of the absolute value of n over n plus 1. You look at a limit like this and you should do at least some work to work out what it is. If you just tell me what it is, I won't be convinced, because we've worked hard in Calc 1 and Calc 2 to calculate this type of limit. The easiest way with polynomials is just to divide top and bottom by n. Or put another way, multiply top and bottom by 1 over n. So I'm multiplying by 1 over n times divided by 1 over n. If I multiply by this quantity, it'll leave me 1 here and 1 plus 1 over n there. And the reason to do that is this limit goes to 0, right? So this limit we can calculate. This is 1 over 1 plus 0. That's clearly 1. What does the ratio test tell us when that ratio is 1? Well, if that ratio is 1, the test is inconclusive. Inconclusive means it's not telling us anything. And for this series, therefore, the one we've looked at here, the one we have a name for, we call it the harmonic series, and it's very important, and you should know it off by heart. You know that the harmonic series diverges. But the ratio test isn't telling us that. Because this is equal to 1, the ratio test is providing no information at all, even though we know the harmonic series diverges. It's entirely possible to get a result like this from a ratio test where the series converges, or where it diverges, or where it's conditionally convergent, right? It's literally telling us nothing. We can make no conclusions. We know from other information that the harmonic series diverges. No test is going to tell you it converges. It's entirely possible for a test like the ratio test to fail. So it's worth noting here, why did the ratio test fail? When does the ratio test fail? Notice the sort of general term we have here. In this case, a sub n is 1 over n, so it's a rational function. It's the ratio of polynomials, polynomial 1 divided by the polynomial n. The ratio test tends to fail, in fact it does fail, for polynomial or rational functions in the general term. Right? If we go back and look at our previous examples, in this case we had an exponential function, not a polynomial, divided by a factorial function, not a polynomial. The test was useful. In this case we had a polynomial divided by an exponential. So the whole thing is not a polynomial or a rational. Right? A sub n here is not a polynomial. It involves a polynomial piece, but there's more than that. It's got an exponential in it. In our next example, there was a factorial in it. Anytime you see terms that involve exponentials or factorials, the ratio test is useful. Anytime you see pure polynomial or rational functions, in other words, polynomial term divided by polynomial term, the ratio test is not going to be useful for us. So that's a useful tip to keep in mind. Let's do one more example. Alrighty, this is a good one, right? Let's start writing this out. There's lots of n's in here. So this is, when n is equals 1, this is 1 to the 1 over 1 factorial, right? Which is literally 1. And then the next term is 2 squared over 2 factorial, and the next term is 3 cubed over 3 factorial, and 4 cubed over 4 factorial, and so on. So, does this series converge or diverge? So if you look at those terms, you might have an answer to that. Let's use the ratio test, right? Let's do the limit as n tends to infinity of the ratio of the n plus 1th term to the nth term. And as you do that, it's worth sitting down separately and working out what kind of terms we've got going on here, because it's not a very straightforward looking general term. So the n plus 1th term is n plus 1 to the power of n plus 1 divided by n plus 1 factorial, and then the reciprocal of the nth term looks like that. Now, we can take the limit here as n goes to infinity and try and simplify a little bit. Well, you know, I've got an n plus 1, and I've kind of grouped here and then expanded. So this term on the top is the expansion of n factorial, and the term on the bottom is the expansion of n plus 1 factorial. And then I've grouped the other terms together, and they're confusing enough, so I'm going to leave them alone for a minute, and at least notice that when I have these factorials, I can cancel the first n terms, and that's going to leave me an n plus 1, right, in the denominator. Well, I've got n plus 1 here to the power of n plus 1, so I'm actually going to be able to cancel this one with one of those. And so we can rewrite this as n plus 1 to the power of n now, divided by n to the power of n. And that, at least, is something we can deal with. That's n plus 1 over n to the power of n. And another way of writing that is just to cancel the n's, and we've got 1 plus 1 over n, and that's all raised to the power of n. And everything's positive here, so I could drop the absolute values. They're not giving us anything, so I can literally remove the absolute values here because I know n is positive, all of these numbers are positive, the absolute values are not adding anything. So we need to calculate that limit. I think you should recognize that limit because this is an indeterminate form of type, well, when n goes to infinity, this is 1 plus 0, and then that term goes to infinity. So it's an indeterminate form of the type 1 to the power of infinity. And we know how to do that. Let's do it. And remember, the idea here is because that's an indeterminate form, when we see that kind of indeterminate form, the best way to do it, to deal with it, is to write it as an exponential of a log, because they cancel out, to the power of n up there. And so then we use the log laws to simplify this. And so we end up bringing that power down out the front. Right, and so we need to look at this limit here. So let's look at that separately. Looking at that piece of the limit, you know, I can take this limit up into the exponential here. Looking at that limit, I can rewrite it. This limit is an indeterminate form of type infinity times 0, because n goes to infinity, that does. But this goes to log of 1, which is 0. And rearranging and writing 1 over n on the bottom instead of n in the numerator, we've got an indeterminate form of type 0 over 0, which means we can apply L'Hopital's rule and differentiate the numerator and the denominator. And doing that, the derivative of log is 1 over, in this case 1 plus 1 over n. The derivative of 1 plus 1 over n is negative 1 over n squared. The derivative in the numerator is negative 1 over n squared, so they cancel. And so simplifying, we get a limit that we can easily take, because 1 over n, as n goes to infinity, that goes to 0. So this is 1 plus 1 over 0. So this is 1. All right, that's great. But remember, this limit in the blue box is what we just calculated, and that's not what we want in this whole calculation. At the end of the day, we want this quantity. So what is the limit as n tends to infinity of that beast? Well, putting it together, it's the limit of e to whatever we got in that blue box, which was 1. So this limit is e to the 1, which is just the number e. And so what does that mean for the series we're interested in? Let's have a look. Well, we found that that limit was 1. It was e to the 1. And e to the 1 is, well, that's just e. That's 2.7. That's bigger than 1. So the series diverges by the ratio test. And that's the idea here. This series diverges. It's worth noting, though, that we could have approached this in a different way. You can show, in fact, that the limit of the general term is not equal to 0. I didn't leave room to write it in the box. But the limit of that general term is not 0. The very fact that those terms are not going to 0 tells us the series diverges right up front. So that's a different way to do it, but you'd have to work out this limit, which goes back to some of the ideas we looked at in 11.1. And we looked at a sequence that was very similar to this. So you might want to review those. All right, thank you for tuning in. Have a go at some of the problems. Have a go at the web work. Come talk to me if you have questions. See you later.